everybody, in today's tutorial we will be looking at acid-base reactions, and my name is Nicole Stanton. So the purpose of today is exploring acid-base reactions and chemical equilibrium. Our learning outcomes will be to 1. Conduct a real experiment, observe an acid-base reaction. 2. Define acids and bases. 3. Explore water as an acid and a base. 4. Calculate the chemical equilibrium of pure water. 5. Investigate the relationship between autoionization, pH, and pOH, and its importance to acidity. 6. Calculate pKa values. And 7. Consider weak acids and buffer solutions. Hi everyone! It's fun to show an experiment of what an acid-base reaction really looks like. We will be looking at baking soda and lemon juice. Baking soda has a pH of 9 and the lemon juice has a pH of 2 to 3. So the pH differences between these are huge, as we know, because of the 10 logarithmic scale. It'll be really interesting to see how they react. Here we go. Ooh. As you can see, it creates tons of bubbles. That's pretty neat. Let's explore acid-base reactions. So first of all, what are acids and bases? Well, acids. When we think of acids, we typically think of sour foods such as lemons. But what really is an acid? It is a substance that releases protons in solution. And then what is a base? Well, they are substances that accept a proton in solution. Now, let's look at water. Water is an acid, and water is also a base. So, what does this mean? Well, the history of this is that in 1923, Bronsted and Lowry defined acids and bases in the same way. A Bronsted-Lowry acid is any species that is capable of donating a proton. A Bronsted-Lowry base is any species that is capable of accepting a proton. So, water enables this transfer of protons as it both accepts and donates protons. It is amphoteric, which means it can act as both a Bronsted-Lowry acid and a Bronsted-Lowry base. So, for example, let's explore this. We will look at this reaction where water is playing the role of an acid. Here, water has donated an H+ to form an OH-, and therefore it is acting as a Bronsted-Lowry acid. Now let's try a practice problem. Looking at this equation, is water playing the role of an acid, a base, or neither in this reaction? Take a moment to think. Here, we can see that water is accepting a proton to form H3O+, and therefore it is acting as a Bronsted-Lowry base. As we can see, acids and bases can react with one another, and therefore water can react with itself. Sounds strange. Well, this is known as the autoionization of water. Water molecules exchange protons with one another. This proton exchange can be written like the following balanced equation. This readily reversible reaction is an example of a dynamic equilibrium. As we can see here, the chemical equilibrium is a state in which the rate of the forward reaction equals the rate of the backward reaction. Now, let's determine how to find the chemical equilibrium of pure water. The first step is to write down our equation. The second step is to write down the equilibrium expression for the autoionization constant. We need to remember that when writing an equilibrium expression, the concentrations of solids and liquids are not included. The third step is inserting the equation. We can calculate the value of K at 25 degrees Celsius using H3O+, which is related to the pH of water. At 25 degrees Celsius, the pH of water is 7. Therefore, we can calculate the concentration of hydronium ions in pure water as so. Step 4 is recognizing the molar ratio. Hydronium and hydroxide form a 1:1 molar ratio during the autoionization of pure water. Therefore, we can use that relationship to calculate the concentration of hydroxide in pure water at 25 degrees Celsius. Step 6. Now that we know OH- and H3O+, we can multiply these values to calculate Kw at 25 degrees Celsius. So this is important to acidity because of the relationship between the autoionization constant pH and pOH. The calculation that Kw equals 10 to the negative 14 at 25 degrees leads us to a new equation as follows. Here we can take the negative log of both sides from our equation to allow us to abbreviate negative log Kw as pKw, which is equal to 14 at 25 degrees Celsius. Therefore, the equation is as follows, and it tells us that the sum of pH and pOH will always be 14 for any aqueous solution at 25 degrees Celsius. So, how can we predict when proton transfer will occur? Well, now we know how proton transfer and acidity concentrations are determined. We will be measuring pKa values. pKa equals negative log Ka. Converting to a pKa simplifies the value. This is done by taking the acid dissociation of a particular acid and taking the negative log of this and converting it to a pKa. The lower the pKa value, the stronger the acid is. And as well, the lower the pKa value, the more stable the conjugate base is. Now, let us use pKa to predict the position of equilibrium, remembering that equilibrium will favor the position of the weaker acid, as we know, the acid with the greater pKa value. We will use the acid-base reaction HCl and H2O. Step 1 is to identify the acid and the base on each side of the equilibrium. In this case, on the left side, our acid is HCl, and then on the right side, our acid is the hydronium ion. Step 2. Now we must compare their pKa values to determine the acidity. Now noting that Ka can be calculated as the ratio of the product of the concentrations of the products to that reactant. So in this case, the following. Step 3. Since HCl is a strong acid, the value of Ka turns out to be very large. Ka equals 10 to the 7 over 1, which is approximately 10 to the 7. Now step 4, therefore the value of pKa is given by the following. Step 5, we apply the same calculation to the conjugate acid on the right and find the pKa is negative 1. Therefore, because the pKa of hydrogen chloride is negative 7, the pKa of the hydronium is higher, and therefore the equilibrium favors the right side. Therefore, HCl is a stronger acid. Now let's see what this means for buffers. A buffer is a solution that is able to resist a change in pH over a given pH range. Now let's talk about why strong acids and also strong bases cannot be used to make a buffer solution. Buffers are made up of a weak acid or a weak base, and buffers are also made up of conjugate salts. So why can't HCl, as we have explored is a strong acid, why can it be used as a buffer? Well, because it is all about how far it goes to dissociation. A strong acid will fully dissociate, meanwhile, a weak acid will only partially dissociate. That is why the arrow is not reversible. So now that conjugate base is not going to react with an acid if I put it in solution. So because if we look at this backwards, chloride reacting with an acid doesn't go backwards to form HCl, and therefore the conjugate base will not react with an acid. Contrastingly, because weak acids only partially dissociate, it has a two-way arrow because it reaches an equilibrium. Are buffers important? Well, yes. For example, buffers are extremely important to living organisms because all biochemical processes proceed normally only when the pH remains close to 7. For example, the pH of blood is maintained as 7.4 by the carbonic acid biocarbonate ion buffering system. It is so critical to maintain the pH of our blood because otherwise cells of the body can stop functioning and the person can die. So today, our purpose was to explore acid-base reactions and chemical equilibrium. Our learning outcomes were 1. Conduct a real experiment to observe an acid-base reaction. 2. Define acid and bases. 3. Explore water as an acid and a base. 4. Calculate the chemical equilibrium of pure water. 5. Investigate the relationship between autoionization, pH, and pOH and its importance to acidity. 6. Calculate pKa values. And 7. Consider weak acids and buffer solutions.